great discovery of gravitational waves from mergers of binary black holes, and of course, subsequently binary neutron stars, which won the Nobel Prize in Physics in 2017. And that was, of course, another great, great window into black hole astrophysics, completely independent from Event Horizon Telescope. But they both teach us about the very strong regime of gravity. So, and of course, these all point to one key concept, existence of black holes, both through gravitational waves and through electromagnetic radiation. We now have the very close or very direct evidence for it. They both point to existence of event horizons, even though you cannot directly see event horizons. You can almost see it. Event Horizon Telescope named their telescope after it. And LIGO can basically probe very close to the event horizon, as we're going to discuss in a minute. And these are predictions of general theory of relativity. So all these observations are great confirmation of Einstein's theory of relativity at this outside black holes, the very strong gravity regime. And this concept of event horizons, as you know, is something that comes up in classical general relativity. And it's basically a boundary of a space-time inside of which, if you get inside of it, you cannot get out. You'll basically inevitably be crushed by the singularity at some point inside. But one of the crucial things that we teach in all our textbooks about, and in our classes about the event horizons, is that in fact, there is nothing special that happens at the event horizon. It is in classical general relativity. It has a global significance. It separates basic observers who are doomed to fall into singularity from observers who have a chance of escaping to infinity. But it doesn't have any local significance. Local observers could live there, at least around the big black hole, and nothing special would happen. At the same time, we have another thing that we teach in our courses, a concept known as black hole thermodynamics that goes back almost 40 years to the work by Bardeen, Carter, and Hawking, and by Bekenstein, and also at around the same time by Bill Unruh, which put black holes on a similar footing as other thermodynamical objects that we are familiar with in everyday world. So the black holes seem to have a temperature, very famously the Hawking temperature, which depends on their surface gravity or surface acceleration. They have an entropy, which depends on their surface area or surface area of their horizons. And they appear to obey, using this temperature and entropy, a first and second law. And these are things that you derive from classical gravity, in fact, even though there are H bars that I guess I've suppressed in these relationships. These are things that are you kind of put by hand. But really, these are results from classical gravity that you could derive using Einstein's basic field equations in vacuum. So the part that's very puzzling about black hole thermodynamics is that anywhere else in thermodynamics, we associate entropy with a number of microstates, basically a counting parameter, entropy of a macroscopic object, like the piece of laptop or computer that is in front of you counts a number of microstates that represent that, that object. But for black holes, even though we do associate entropy and temperature to it, we don't know what states you are actually counting. And this is one of the greatest mystery of quantum gravity, that it seems to know the entropy of the black hole, but we don't know what it is representing. So what is wrong with this classical notion of horizons? Now, I'm giving you, the list in fact is longer, but I'll give you just three most significant ones from my point of view. The one that everybody, at least most people are familiar with, is known as the information paradox. That was originally due to Hawking, but it's kind of been reinvented and relabeled in various forms over the past basically 3 or 4 decades. So the information paradox, basically the most modern version of it says that if you believe black hole evaporation, which is something that comes out of black hole thermodynamics, black holes are hot, as we discussed, so they could evaporate in vacuum at least. But it's not clear what happens to the information that fell into the black hole. It seems that a unitary evolution, as you expect from ordinary quantum mechanics, cannot be consistent with local physics and the presence of a smooth horizon. So this is something I'm going to talk about a little bit more, but this is kind of the biggest and most well-known problem known as the information paradox or the firewall paradox that we're going to get back to. Another flavor of the basically problem with the horizons, classical horizons, is that it is a classical notion, and we know that classical physics is always an approximation to a more complete quantum picture. You usually think that quantum corrections in big things are not important. And the way to quantify that is you look at the action. And usually, basically, if you think about in the path integral formulation, whenever you have a big action, it oscillates a lot. And basically, there's a lot of cancellations. So what dominates the processes are the extrema of the action, which are the classical solutions. However, there could be things that happen that are not on the extrema. They're just suppressed exponentially. And the way this is formally quantified is exponential of minus Euclidean action, which quantifies, basically tells you what is the tunneling probability. So, I mean, I'm standing here in front of this laptop, but there is always a probability, according to quantum mechanics, that I just show up in front of you wherever you're sitting in Israel or Brazil or Japan. So that's not disallowed in quantum mechanics. It's something that known as quantum tunneling. And it could, it's just an exponentially suppressed process. And you could estimate this by basically e to the minus something known as the Euclidean action that quantifies basically the probability of crossing a barrier. The bigger the barrier or the bigger the object, the bigger is this Euclidean action. Now, you can ask the same thing about the black holes. So the big black holes have big Euclidean actions. But then if you say black holes have huge entropy, and that's the other thing that's unique about black holes, is that they have bigger entropy than anything else we know. The entropy in black holes, even though the mass in the black holes in the universe is much smaller than other things, like dark matter, for example, or radiation, their entropy dwarfs entropy of anything else in the universe by many, many orders of magnitude. So the entropy that Hawking basically discovered, Beckerston-Hawking entropy, is much bigger than anything else. And the weird, bizarre coincidence that, in fact, if you calculate Euclidean action, if you calculate entropy, they happen and multiply basically them by each other, because if something is exponentially suppressed, you can say, okay, so tunneling to one state is exponentially suppressed, but how many states can you tunnel to? And the number of states is exponential of the entropy that you could tunnel to. And this product is, in fact, exactly cancel each other. This is something of order 1. So it suggests that if you have a star that collapses into a black hole at some point when you form a horizon, you actually have order 1 probability of tunneling to some non-classical state. And the final motivation that got me started on this has to do with dark energy, but it suggests, and I'm not going to go into any details of this, but it suggested that you could expand the scale of dark energy. But that requires getting rid of the horizons and putting something more exotic near the horizon of the black holes. And that naturally relates the scale of dark energy to a scale of the mass scale of a stellar black holes. Okay, so a little bit more about the information paradox. This is known as the firewall paradox. It became popularized by Almeri, Marov, Polchinski, and Solly, late Joe Polchinski. And it basically, although this is a version of what Samir Mathur had already put forward a few years earlier, but it's basically formalizes this idea that these 4 notions that are all each on its own is taken as mainstream. They are cannot be all valid at the same time. The first is unitarity of quantum mechanics, and if you believe there's a theory of quantum gravity that follows the same rules. That's number one. Number two is equivalence principle or no drama at the horizon. So what I just mentioned, that if you fall through a horizon of a big black hole, nothing should happen. The third one is that the quantum field theory, basically what we test in LHC, Large Hadron Collider, should be valid everywhere beyond the Planck length away from the horizon. So basically outside the horizon of the black hole, you should be able to use quantum field theory as we know it. And finally, that the entropy of black holes is given by the area, which basically equivalent to saying that the dimension of the Hilbert space of a black hole is exponential of the area over 4. So this is basically a statement that you really think the Bekenstein-Hawking entropy of the black hole is the entropy, is the thermodynamic entropy that we define in quantum mechanics. And they say that even though each of these on their own are usually thought to be true, often with no direct evidence, but nevertheless, they're all assumed to be true, they cannot all be consistent for black holes. And in particular, they suggested that the easiest one to relax would be this equivalence principle or no drama at the horizon, which suggests basically is replacing classical horizons by a firewall. So this is the theoretical motivation. And there has been, I think, thousands of papers arguing back and forth on whether this makes sense or not. And to be honest, I think the answer to this doesn't come from theory, or will not come from theory. It will come from experiment. So if you think something special might happen at the horizon, the way to test it is what basically we got excited to work on. And it was first suggested by Vitor Cardoso and his collaborators back in 2016, basically less than a month after LIGO's discovery of the first binary black hole merger. And this is a figure from the original paper. So what they suggested, and this is kind of a picture that shows it, is that if you have an object or some structure like a firewall that's near the horizon of the black hole, and then you have the photonosphere, or photon ring, or the angular momentum barrier, you could have gravitational waves that get trapped between these. But they normally would just fall through the horizon because you don't have a firewall in standard gravity. If you do have something that has non-trivial interaction with gravitational waves, then you could have basically waves that get trapped between these two barriers. However, the time it takes actually to go from angular momentum barrier to the firewall would be logarithmically long, because I mean, as far as the observers at infinity are concerned, it takes infinite time to reach the horizon. This is not quite at the horizon, but because the quantum effect, it would be a Planck length outside the horizon. So the time is long, but only logarithmically long. For the first binary black hole event, if you actually compute this time, then you get around 0.3 seconds, which is, I don't have a time scale here, but it would be like just outside this window that's shown usually in LIGO papers. So it's a time that's long, but it's not very long. It's something that's very, very testable. And so this is basically this is what we call the echoes from MAPIS, and I'm going to come back to basically retesting this and the status of the test. But then the other question you want to ask is, okay, so what happens at this firewall? And a priori, the theorists don't tell you anything. In fact, they cannot even argue, they cannot even agree whether anything can reflect off the firewall or not. Everybody has their own kind of prejudice. We kind of course, we are not separate from that. We all have our own prejudices as well. But
can I ask a question?
Yes, go ahead.
Just to make sure that I understand the model. So the firewall is close to the horizon itself?
That's right.
So how did you get the 0.3 seconds? I'm not sure that I got.
Yeah, so the idea is that the firewall is a Planck length outside the horizon.
Okay.
So if it was just on the horizon, then it would take infinite time to get there.
All right, so this is just a Planck length above the horizon.
That's right, just the Planck length above the horizon. So because it's a Planck length, then it's not exactly infinite. It's actually logarithmically long. It's basically log of the size of the black hole divided by the Planck length.
Right, but then you could have, okay, don't you have another correction of a logarithmic nature that could give you another order of magnitude?
What other correction are you talking about?
Well, that's what I'm trying to figure out.
So this log term comes basically from switching to the tortoise coordinate, going to the Planck length and back.
Mm-hmm.
Okay, fine. Go on.
Yeah, so this is just the, I mean, if you just find look at the radial geodesic that falls to the horizon and comes back, this is just comes out of that. And in fact, the spin dependence is not hard to capture. Yet there are order 1 corrections to the log that are hard to model and very model dependent. But the leading log is, you can actually compute it very precisely. And the prefactor, I'm going to come back to that, is in fact just 1 over surface gravity, or 1 over the temperature of the black hole is this prefactor. So in the limit of spin going to 1, in fact, this time goes to infinity. But for any finite spin, this time is finite. Okay. So, so then the other question is, how much reflectivity do you expect? Now, if you go back to the image of the Event Horizon Telescope, for example, you saw a black dot, black hole in the middle. That's what the name says, a black hole, right? Does that mean that black holes are exactly black? So if there is any reflection, why don't we see it in the Event Horizon Telescope? And there must be a good answer to this. Of course, one may argue that, okay, so the Event Horizon Telescope has already ruled out this firewall business, or for reflectivity of firewalls. But we believe there is a more rigorous answer to it, which basically that the reflectivity should be frequency dependent. And in fact, the frequency dependence of the is something that can be calculated from first principles. And we have argued this is another universal property of the horizons. So as I mentioned before, temperature, horizons have temperature and entropy. That is the universal property. And we have all these, we have basically 3 independent lines of argument with Naritaka Oshita, who is, I think, in the audience, and my PhD student, Singwen Wang. We have 2 papers that actually we argued this in detail, that there are 3 different lines of argument based on fluctuation dissipation theorem, based on thermodynamic detail balance, and also based on CP symmetry, that they predict the reflectivity of the horizon without any free parameters. And they just give it to be a Boltzmann factor, e to the minus h bar omega over kt, where h bar omega is the frequency, where omega is the frequency of the gravitational waves. Or in fact, any incident wave. It doesn't have to be gravitational wave. It could be photons. It could be neutrinos. And this would simply say that the reason Event Horizon Telescope is not seeing anything coming out is that the frequency of the photons that you see coming, or that are probed by the Event Horizon Telescope, are much, much higher than the frequency of Hawking photons, which have that have wavelength comparable to the size of the black hole. So in fact, gravitational waves are the only known particles or known waves that have comparable wavelength to the size of the black hole, comparable frequency to the Hawking temperature, and can be probed, basically can reach Earth. Photons, basically, you need to go below the plasma frequency, so you cannot actually see something comparable to KT. And neutrinos, you just cannot see them at low frequency and low energies. They're just invisible because they're weakly interacting. So, and in fact, the picture to keep that we promote, and we give several lines of argument for it is that echoes are a stimulated Hawking radiation. So the Hawking radiation, so this is a, yes?
Yeah, I just continuing on that. I mean,
yes.
What about more, you're talking about gravitational wave echoes.
Yes.
But in that, if this exists, then you'd expect echoes also from, normal radiation and possibly normal matter that falls into black holes. So where is the signal that you should see in, active galactic nuclei or other, black holes?
Exactly. That was the point I was making, is that you have to be able to probe low frequencies. So if you could see and low energies, and the only one place that we can actually do that is with gravitational waves. So with active galactic nuclei, so for example, you think about MHD waves, for example. So So MHD waves could have low frequencies, but they don't propagate with the speed of light. They propagate with, say, magnetosonic speeds. So their effective horizon is in fact outside the event horizon, so they wouldn't actually probe anything that happens near the horizon. The photons, on the other hand, they propagate with the speed of light, but in fact, in the plasma, they have a plasma frequency. And to actually probe this regime, you need to go below the plasma frequency, which is not possible. I mean, at least in astrophysical black holes. So it's just not, I mean, in principle, this should happen for any type of particle or wave, but the gravitational waves are the only ones that are practical because they are weakly interacting with everything. And everything else is either basically become the strongly interacting or just, like neutrinos is one example, but they just invisible at these low frequencies. Okay?
So Niayesh, there is the intermediate regime where there's some type of radiation falling into the black hole and it echoes out, and we cannot see it because, you know, we only see radio and X-ray and stuff that is way, way away from the band where this would be echoed. But then some of that radiation might still carry energy away, carry angular momentum away, and we can maybe quantify the back reaction on the black hole from those echoes.
Right, but I see the point I was making is that even radiation, even low frequency, even if we had like very low frequency radio telescopes, these photons cannot actually come out because there's a plasma frequency around all black holes. And because basically whenever you have ionized plasma, there is a minimum frequency that electromagnetic radiation could have. And that's orders of magnitude higher than the Hawking temperature, as it turns out. Well, I mean, sometimes it can be close, but in fact, it's usually orders of magnitude higher. So these photons cannot even propagate. Basically, it gives photons a mass. That's what happens.
What material?
Sorry, what's that?
What material? Matter.
Like what matter?
Gas that would fall in.
Yeah. So I mean,
quite close to the speed of light once you get to these distances.
Right. I mean, usually with gas, if you have a finite speed, there's a sonic point that whatever happens beyond it, nothing can get out, right? Yeah. So okay.
You get close to the Keplerian velocities, which are very close to the speed of light, right?
Yeah, it is close, but so I mean, for example, if you think about accretion disks, accretion disks, they all have a basically sonic point. Basically, you are subsonic on one side, a supersonic on the other side, and whatever happens downstream cannot get out because you're basically going down supersonically. And yeah, so I mean, it would be great if there is a way to test this. It's just I haven't been able to come up with one. There is probably something, if there's a gas falling to this firewall, something would be happening close to the firewall. But how much of it can get out? I think that's a good question, and I don't think we have a good answer to that. But I mean, I think it's something that hasn't been explored. And what we've done is very simplistic in terms of this. We just looked at single particle interactions with the horizon. So what I was going to say was that if you want to think, so the way to understand this reflectivity is to think about basically the way you understand lasers, which is through a simulated emission. So, so what Hawking showed us, was that if you just put a black hole in vacuum and let it sit there, it doesn't just sit there, it radiates, Hawking radiation. And if you think about this black hole as a quantum object, this is like a spontaneous emission. You have an excited system, and it's kind of decays to lower and lower levels, and it keeps emitting photons or gravitons or all sorts of particles. Right? It's just like an excited atom. And this is a spontaneous because it's just sitting in vacuum. Now, if you put the same atom in an environment like you do in laser, where you have a lot of frequencies, a lot of photons of the frequency that could excite or de-excite this atom, then you can get a stimulated emission, which means that you can get much faster decay than what you had in vacuum. And this is basically what we are arguing is what could be happening with echoes. That basically the same way that if you put an atom inside a laser and you have a lot of atoms that are basically being excited at the same frequency, then that could stimulate the transition. The same thing could be happening with echoes, that the Hawking radiation is very, very weak on its own. But if you have incident gravitational waves, which could be happening during the mergers, then you can stimulate Hawking emission. And then that would, but that only happens at low frequencies. At high frequencies, that wouldn't happen. And that's something that basically we showed. And this reflectivity is something that you could think about as stimulated Hawking radiation. So
is this a phenomenological argument? I would think of it as stimulated emission. Or do you have an actual model for how the stimulation works?
So we have these calculations. In particular, the thermodynamic detail balance is basically we just repeated the calculation that Einstein did for detail balance for this Einstein's A and B coefficients. So we just repeated his calculation and just plugged in the properties of the black hole, and we got this. So there is one assumption here, which is assumption of weak interaction, which is the same assumption that you make in the atoms. It's a perturbative expansion. And the idea is that for low enough frequencies, that assumption of weak interaction is valid, which of course may not be true, but if it is true, then this is what comes out. So there is no phenomenological assumption here. I mean, there is a theoretical assumption, which is weak, basically weak coupling assumption, which is the same assumption you make when you basically couple an atom to laser, assume that the coupling is weak. Now, for black holes, you may think it may not be correct. And I think probably for high frequencies, it's certainly not correct. But for low enough frequencies, it could be correct. And we have these other arguments that are different, but they still give you the same result. So this gives us some confidence that this may be, there might be some truth to this. But yeah, it is, I mean, partly phenomenological in some sense, you may argue. But it's really based on these theoretical arguments. And as you can see, there is no free parameter here. So this just comes out of these derivations. So of course, I mean, as I said, any calculation that's good as the assumptions it makes, and the assumptions could be wrong, and they should be tested. So interestingly, this time scale of echoes is something that's been going around or echoing around, forgive the pun, echoing around the theoretical circles for basically many years before we came along, or we started thinking about it. And this is goes back to, in fact, Sakino and Susskind, who's Susskind is one of the forefathers of the string theory, who suggested that black holes are fast scramblers. And he suggested a time scale for fast scrambling. Basically, they suggested the black holes can scramble information faster than anything else in the universe. And the time scale is, in fact, given by some constant of order 1 times a time scale divided by beta. Beta is 1 over temperature. So this prefactor, in fact, exactly the same prefactor that we have for echoes. Times log of the number of qubits, the number of degrees of freedom. So this time scale for scrambling is, in fact, exactly the same time as echo time, up to factors of order 1, which is kind of surprising when I first noticed it. And I asked my student, Krishan Saraswat, to look into it. And in fact, he looked into this, and he showed that exactly in all the contexts, various types of black holes, various types of dimensions, the concepts of fast scrambling, which is something that's a very hot topic in quantum information and in holography, coincides exactly with the time scale of gravitational wave echoes. So it's kind of interesting that these two concepts that came from very different kind of circles happen to coincide with each other. Now, this gives me some hope, although it's far from any confidence, that there could be a holographic understanding of echoes. If you have ever talked to any string theorists in the past 20 years, that's kind of the thing they're most excited about, and that's the thing they use to understand anything that's, well, they can understand, to be honest. And so if there is a holographic picture of these echoes in terms of some boundary quantum theory, that would be something that would be easier. It gives us basically more tools to study. And so they have some ideas. The paper I just mentioned in the previous slide by Krish and Saraswat, we suggest that it might be seeing these echoes in the out of time order correlators of correlators of operators in the boundary. And we have a paper coming up with Ramit Day in India, who's connects echoes to the Kerr CFD correspondence, which is a different holographic description of black holes. So I'm not going to talk much about that. So let me briefly talk about pandemics, which is what I promised and got me very excited. Well, I mean, of course, people are dying. That's not good. But it turns out that there are interesting patterns that emerge. And if you kind of look at, I mean, I just downloaded this yesterday from Harvard in data. This is the total number of confirmed deaths, which is, of course, very unfortunate for COVID-19. And if you can see, there's this kind of big hump from what happened in China, and then there's this another hump for what happened in the world. And you could look at the doubling time, which was very short at the onset of the epidemic. Then the China epidemic got contained, so the doubling time became large. But then suddenly it started everywhere else, so doubling time became short again. And then now it seems that it's become contained again. So you see these kind of two peaks. And what I did was I just downloaded the data and I inverted this to look at the growth rate, basically 1 over this doubling time. And on the left, you see this basically daily mortality growth rate, which is d by dt of log of daily mortality, although I did some averaging over a 2-week period, so that doesn't wiggle too much. And you see there's a peak for China that happened in early January. And then there's another peak basically when it's happening basically in mid-March across the board. And if you look at the difference between these two peaks is actually just log of the number of the humans in the world, 8 billion, divided by this maximum here, maximum growth rate, which happens to be exactly the same time scale as for echoes. So this is the echoes for GW 150914, which is log of the number of cubics, log of the entropy divided by this maximum, in this case, decay rate. And you will say, okay, I'm kind of connecting things that have nothing to do with each other, except that what these are really just exponentials. This is the growing exponential, is what an epidemic is. And this is a decaying exponential, which is what quasi-normal modes of the black holes are. And basically what these time scales are something that basically tells you about non-perturbative effect that can happen when you have exponentials present in the problem. So this time scale tells you that if you have one person infected in the world and nothing happens, there's no intervention, then within this time, the whole world will get infected. And so that says that no matter how much intervention you do, how much quarantine you do, I mean, even if you miss 1% somehow, then over this time, that's going to grow into the entire world. So that's just simple, I mean, just what an exponential is. Right? And what this echo time is, and that's kind of the way you can understand the log from forgetting about anything about gravity and horizons, is that if you have something exponential decay, which is what's happening at the end of at the ring down of the black hole, then within this time, that decay basically becomes aboard the Planck scale. Basically, the classical effects become less than the quantum effects because the classical things are decaying exponentially, and at some point, basically after this time, the quantum effects become bigger than quantum effects become order h bar or order h bar. But the classical effects become less than that. So that's kind of the way of understanding why these scales happen to be the same. And now, how much you could push this? I mean, this echo, we know it repeats again if I keep, now whether that means that we're gonna have another peak of epidemic, I don't know, I'm not gonna go there. But anyway, so I thought it was a cool picture. And it has to do with basically what exponentials do to large systems. Okay, so quantum black holes in the sky. Now, this is a controversial topic. This is something that got us started. So I guess if you want to take away one thing from this was that from this talk is you may not be convinced that there are echoes in the data, but what you may be convinced of is that looking for echoes in LIGO is basically the same initiative as looking for Higgs, for example, in Large Hadron Collider. Since that they have the same motivations, actually very, very parallel motivations. So Higgs was really necessary part of a standard model. I mean, a standard model was fine. There was no evidence for it prior to discovery of Higgs. But if you want it to be a consistent model that obeyed unitarity, perturbative effective field theory, and gauge symmetries of a standard model, then Higgs should have been there. I mean, a standard model without the Higgs is not a consistent theory in quantum mechanics. You either get a strong coupling, or you have to violate unitarity, or you have to violate gauge symmetry. So, or some combination of it. Now, the reason we look for echoes in LIGO is exactly the same, basically, is that you want black hole evolution to be unitary. You want perturbations to be, you want your field theory to be perturbative. And instead of gauge symmetries of a standard model, you have the gauge symmetry of gravity, which is diffeomorphism invariant. And in particular, it implies the entropy of a black hole, which is the holographic entropy bound. So of course, I mean, we did find Higgs in LHC. We didn't have to. We might have found some more complicated things here, or no Higgs at all. And the same could be true with LHC, that that we may or may not find echoes in the real data, but this is the same motivation. So the real solution to these problems may be more complicated or less complicated. And a few years ago, we actually looked for them. There's some tentative hint of it in data around p-value of 1% that Ofek and his collaborators also looked into. Let me see. So this is Jahed, who led this effort, and with Hannah Daikar. So Jahed, probably some of you know him. He's now a postdoc at AEI. Hannah is now, she was an undergraduate at McGill, now a PhD student at CETA, University of Toronto. So not as many people know Hannah, but probably you know her mother, who in this picture is accepting the Nobel Prize from the King of Sweden. And yeah, so she, I guess, obviously Hannah will be the next person who's going to win the Nobel Prize after her mother. So moving on, now what happened with this echo business? I'm not going to talk too much about this. So the way we believe things is not by, I mean, one observation or two, but really through preponderance of evidence. And the case with echoes is kind of complicated now, because it's, I mean, there seems to be I think I would argue there is preponderance of evidence, but it's very confusing evidence. So here we have a list of kind of works that reported positive evidence, but p-value less than 5%, and then the ones that have reported negative evidence, which is, I guess, anything above the p-value of 5%. So, so the case is, so some of these groups are not independent, and some are the same. But basically, an interesting thing is that so there are p-values around a few percent. So I think, let me see. One of these is OFX. I think, OFX, are you on this one as well, or are you on both of these?
I'm on all the Vestovec and Nielsen papers, which
Okay,
we consider to be null or negative evidence.
That's right, and they consider it to be null or negative. Although I mean the p-values are about at least the ones that for the same set of data and models that we looked at, the p-values they repel is 2%, or well 2 to 4%, right? For this one. For this one is actually complicated because I think they have a disagreement on the first one because I think it's inconsistent with your previous paper. So I don't think we quite get a resolution on this, but these two, in terms of one of the events, is not consistent. But anyway, so that's the topic that, as I said, is very controversial. So, so the gist of it is that there are some p-values around a few percent, and there are a couple of groups, including Jahed and I, for binary neutron star, and then the Toronto group, or the, formerly Toronto group, who claim basically much more significant. In fact, now you could watch Bob Holdham's talk. He claimed a p-value of 10 to the minus 10, which is ridiculously small. But anyway, so the question is who exactly to believe here. But there's a range of p-values. And another interesting, there are these interesting kind of complementary lines of evidence where I'm going to come back to Salami et al. In a minute. So that seems to be confirming Abedi, Darkar, and my paper. But also there's an Astro modeling of binary neutron star that gives you basically a formation of black hole time that's exactly the same as the echo time that we observe. So that's I think these are kind of interesting. But then at the same side, so here I'm quoting also Offek's paper. So they also say they don't find evidence, but then they actually do, what they do is that they either change the prior or make other assumptions about the prior. So that's the story. And yeah, so I mean, as I said, so the story, and then others, other groups also have looked at it, and depending on exactly what they looked for, they didn't find it. So some of these are the same groups that are listed in the previous page. But basically, depending on exactly what they search for or which events they search for, they didn't find anything in this page. Okay, so if you want to learn more, read more about us, actually, this is the example I was talking about. So here's the abstract of Salami et al. Paper, which is a completely independent paper from what we did, and it is in 2019. And in the abstract, they claim that they see evidence of post-merger signal at 0.2 second and 0.1 second. For these two events, and this was our prediction from 2016, where we basically predicted the time of the echoes based on the properties of these LIGO black holes. And as you can see, these two times happen to coincide exactly with the times that's reported here, even though this is a theoretical prediction and these are actually just observations. So, and if you want to read more about the controversies and all basically various sides of the argument, of course, from our point of view, you could read this review article. And also there are two conferences that you could watch their talks online. There's I've linked both of them down here. So moving on to the last part of the talk, which was the main subject, is the quantum black hole seismology, which is kind of what's happening now. And this is a work mostly with Naritaka Oshita, who's a postdoc or JSPS fellow and a postdoc at Perimeter Institute. And this is Daiichi Suno. I couldn't find his picture online. So this was like one that Google gave me. So I thought it looked similar enough. Daiichi, are you there?
Yeah.
I don't know what happened. There is Daiichi, because that was a real picture of Daiichi up there if you saw him. But yeah, this is not real, but I think it was close enough. I think I should have asked for a real picture. Sorry, my son here is putting on a gecko costume. I have to help him with it. Okay, so good. Yep. Now, so what's the story of seismology? Now, the topic of black hole spectroscopy is one that's been written about a lot, and is basically probing the quasi-normal modes of the black holes, the same sense that you do it in general relativity. So the black holes, as they ring down, they have a bunch of quasi-normal modes. And a spectroscopy is basically trying to pin down these various quasi-normal modes. But as you know, in standard quasi-normals of black holes are in fact mostly located around the angular momentum barrier or the photon ring. So similar to the spectroscopy of atoms, where you actually probing the orbits of the electrons, which are outside the nucleus, and the spectroscopy of black holes is not actually probing the horizon, but rather probing the photon ring. In the other hand, seismology, for example, for stars or the Earth or the sun, probes the inner structure of the object. So what we call seismology is in fact probe of the basically near horizon, near the event horizon, or whatever replaces near the event horizon. Okay. Right. So that's black hole seismology. And basically what we've shown in this couple of papers is that you could probe various properties of the near horizon structure or firewall by looking at the spectra of the gravitational waves. So assuming that you have good enough information, or good enough, of course, if there is anything sitting there, if you have good enough signal. Sorry, I need to take a minute. I think there's something going on. So just give me a minute. Sorry, I think there's stuff happening here that I'm.
Sure,
I'll be
sure.
back in a second.
We understand. Well, while he is away, I can tell you that most of the AI group, of which I was a part, of course, disagreed with Nash's and Jahed's results on echoes, but Jahed later took up a position at the AI and is there right now. So this scientific debate is actually ongoing with parties exchanging visits and long-term positions to kind of iron out their differences and hopefully reach an agreed or at least agree to understand the differences between our results.
Yeah, I think that's a very good way of putting it. I'm hoping that with better data, basically, this becomes an obsolete debate, and that's usually the case. That whenever we have to argue about the statistics, it means we just need better data, and hopefully better data will shed light on a situation. But when we do get better data, then we can look at the spectrum of the data we get, and then we can learn about various properties of anything that could be sitting there, if there is anything that's sitting there. And for example, we could distinguish between the constant reflectivity and Boltzmann reflectivity that I mentioned. So for example, Boltzmann reflectivity, you would get peaks near the horizon frequency for higher harmonics. For lower harmonics, or for m equal to 0, I guess I should say, you don't get peaks near the horizon frequency. And depending on the model, you either get, for constant reflectivity, you get similar peaks at all frequencies. For Boltzmann, you get higher peaks at lower frequencies, as you expect. And in fact, what the Boltzmann does, as you notice this omega tilde here, what it does is it gives most reflectivity for the frequency near the m times the horizon frequency. So that's where the peak always is in reflection if you have Boltzmann reflectivity. So if you could measure this spectrum, then that tells us about, it could tell you which harmonic is most excited, and it could also tell you which model of reflectivity might be a more correct model of reflectivity. Here you notice we also, I put a TQH. In fact, it turns out, I mean, even though the Hawking temperature is what we derive, it could be that this is a phenomenological parameter that should be measured. So for if T goes to infinity, then you have a perfectly reflecting ball. If it goes to 0, then everything essentially is absorbed. And this is another thing that you could imagine could be something you measure. You call it the quantum horizon temperature. You could measure whether you're dealing with an exotic compact object or a modified dispersion relation. Sorry, there is a gecko costume here, which doesn't seem to fit very well. So for example, if you have an object with a modified dispersion relation, which is something I can give you echoes, you would see a bunch of harmonics. So these are basically peaks. And I should say something actually which maybe wasn't clear. I should go back somewhere here. So what we're talking about, so what we're talking about here is that you really have a cavity or an echo chamber. So you have basically modes that are trapped between these two barriers. And then whenever you have basically an echo chamber or a cavity, you have all the natural frequencies that could sit in there. And those are where we have the peaks. Of course, they are not infinitely sharp because things can leak out either this way or that way. It could be absorbed here, or they could leak out this way. But those are really what we're looking at. So the subject of seismology is just looking for natural frequencies that are sit in between these two barriers. And that's what, right, so that's what we were talking about. But exactly where these peaks are, which are basically these natural frequencies of this echo chamber, it does depend on exactly the properties of that, the modes that you're exciting, and also on what harmonics being excited. It does depend on exactly what's responsible for the reflection. So if you have modified the spread relation, the position of the echo chamber or the wall would actually change position of reflection. If you have an exotic compact object, it's always the same. So by looking at basically the bunching up of the modes, you could actually tell which one of these you're talking about or looking at. You could also figure out whether you're exciting mostly the overtones, and there are some evidence from simulations that suggests that might be happening at this near the merger, or the fundamental. And actually that makes a big difference for the echoes that we've explored in our paper. And for Boltzmann reflectivity or constant reflectivity, in fact, you get bigger echoes if you could excite the overtones rather than the fundamentals. And finally, you could also probe the phase of reflection, because you may get a phase at the reflection, and that actually moves around the position of the harmonics. So I should mention that there is this is actually a separate work that we're doing with Luis, who's actually joining us as well, and his supervisors, Cecilia Chirenti in Brazil. And here we're actually doing a more first principle calculation of echoes by solving the gravitational wave radiation from an inspiraling point mass. So here we're talking basically this is formally valid only in the extreme mass ratio, but it's where you can actually trust the calculation all the way from in spiral to merger. And here's basically the spectrogram of the echoes that he's calculated, and Luis just sent me at 2 in the morning or 4 in the morning, I guess, this morning. And this is the spiral that you all see in love in LIGO, although they're slightly different colors. And these are the echoes, and these are the echoes that you see, depending on the temperature that you assume for the quantum horizon. So you could see you could get more pronounced echoes or less pronounced echoes, depending on the temperature that you assume. And he actually has also quantified how the mass ratio affects the amplitude of echoes. And it's interesting that what he finds is, sorry, I cannot do it. It's interesting that the mass ratio is, I think there's a national cutoff to this. I have a more stricter chair here. So the amplitude of echoes increases. Azad, you should tell Paris to give it to you. Oh, sorry, I'm busy. Okay. Do you want to see Ofek here? You don't want to see Ofek here? Come see. Come here. No? Okay, sorry. So the amplitude of echoes increases with larger mass ratio. Okay, come here. Okay, so
Hello.
Okay, you want to say hi? No? That's awful. It's got a nice beard. I don't have a beard. It's got a very nice beard and mustache. So the last thing I wanted to mention was, so this is our last paper with Daichi and Naritaka. Is sorry, I cannot do it. Yeah, this is the problem with giving talks at home.
Yeah.
I hope you bear with me. So apologies. So we can
if you need to go, you can go. You know, we fully understand the situation that we are all in these days.
Well, as long as you can hear me, I think it's okay. We'll see how. I think it'll be. I mean, it's the last couple of slides. So we basically now can compare this Boltzmann echo model or the seismology models that we've developed with the tentative observation that Jahad and I made for these harmonics from binary neutron star merger, or presumably the black hole that would have formed at that point. And basically, depending on the properties of the model, they could match. So if you look here, depending on basically which overtones you excite and which model, this is the constant reflection, this is Boltzmann reflection, then you could actually match the data. Okay, so then we could, in principle, and this was Niayesh's idea, to look for, we could look for failed supernova. And I have this idea that, in fact, this event that I don't know, apparently still online, could be a failed supernova echo that are being seen. Azad, sorry.
By a failed supernova, you mean a star that's trying to explode but cannot penetrate outside of the stellar envelope?
That's right, yeah. So these would be electromagnetically dim, but of course, if they do form a black hole, then they would form gravitational wave ring downs, and they would form echoes in principle as well, right? That's quite funny. What's happening here? So that's the idea, and the main thing here, if you have something with a few solar mass of the black hole, a few solar mass black hole, then in fact its ring down frequency would be beyond. It would be a few kilohertz. It would be beyond LIGO sensitivity unless it's very close by, and this is why we haven't actually seen any ring down signal or merger signal from binary neutron star merger. But the echoes would be much lower frequencies, the echo harmonics. So they could be actually very well detectable. And this is kind of our most optimistic scenario, that you could actually see these even with current LIGO up to 10 megaparsecs. And the next generations could actually push this onto up to 100 megaparsecs. So depending on the spin, of course. Anyway, so I don't know. Do you guys have a better model for this now? What happened, or maybe has it gone away?
We're so busy working on the confirmed events for publication, we don't even get to do the unmodeled or unknown sources.
I see.
That's up for people in the world to research.
I see. But is the data public on this?
Probably not yet. If it's not a confirmed event, then no events have been public. The catalog will be issued, hopefully. It was supposed to come out in May, but because of the situation, it's postponed probably to the summer. That will be the first catalog, and there'll be another catalog in about 6 months to a year cadence for the rest of the 03 LIGO observation run. So the data will become public, but it will take a while.
So,
but I do want to ask you about the failed supernova. If a black hole is formed inside, even if we can't see the massive explosion, would it then not gobble up the rest of the star?
Yes, it would. Yeah.
So we should see a failed supernova, a remnant, feeding up and feeding a disk and making jets and all that stuff.
Well, there would be some signal. The question is how pronounced. The question is how much of a fallback disk will you get? And there are some candidates for these failed supernovae. So basically, the idea is that these are not basically huge explosions. There would be some brightening, but not nearly as dramatic as that of a supernova. And there should be a fallback like this. But I mean, you see, the thing is, the supernovae are very, very super Eddington events, right? Because they are very high density, very short time. Most of the cooling is through neutrino emission. The ordinary accretion that happens afterwards, this is kind of much milder. And even if it's there, it's going to be much harder to see, right? It's not going to be as dramatic. So like the binary black holes, like extra binaries that we see most of them only in our galaxy. I think maybe we see one in LMC. I don't remember exactly. But of course, supernovae, we could see them much farther away. So it's a good question. If something is around 10 megaparsec or a few megaparsec, would we see a failed supernova at that distance? I'm not 100% sure, and I actually maybe Daiichi knows the answer to that. Do you know how far we are expected to see this failed supernovae?
Maybe a rough estimate is about like 10 megaparsecs.
Is from electromagnetic radiation? You say we can see them up to 10 megaparsec?
Yeah, so before the neutron star collapses to the black hole, there will be neutrino radiation that basically makes the core lighter, and that basically releases some gravitational energy, as you would call it. So it'll make some fraction of the outer envelope unbound, and that can emit some weak radiation that can be observed somewhere around 10 megaparsec, I would say.
Are you talking about gravitational wave radiation or electromagnetic radiation?
Electromagnetic.
Electromagnetic.
Basically in the infrared and optical.
Right. Yeah, that's right. And indeed, there are some candidates for this, but I mean, I think they are just candidates. Right. Good. So it would be good. I mean, if there is a way to observe this in, of course, gravitational waves and echoes, that would be, of course, interesting possibility. So, I mean, I've gone way over time. Sorry for the interruptions. That's so. This is it. So quantum. So the conclusion: quantum black holes may be much more interesting than their classical counterparts, and in very testable ways. The logarithmically delayed echoes that I talked about, they appear in diverse contexts, so from quantum black holes, but also in quantum information, and also in pandemics. So it's interesting that this concept of echoes or logarithmically delayed echoes is something that's universal across various concepts or contexts, quantum or even classical. And there is tantalizing, though controversial hints for echoes in LIGO. And as I said, we need better data and I guess more interactions to reach some consensus. Black hole seismology is a systematic way to probe quantum structure of black holes. And this is one that's been primarily spearheaded by Daiichi and Naritaka, although I've been happy to cheerlead. And I said, the last thing, I don't know, at 5 in the morning, this sounded like a good last, last line. Don't ask what echoes can do for you, ask what you can do for echoes. There you go. Okay, thank you.
Thank you, Niayesh.
Thanks.
Any further questions from the audience?
I have a very basic question, maybe, about this echo. If you can go back, right? There is a reflection between two boundaries, right? One boundary, as you said, is the Planck scale, which is above the horizon, right?
Yes.
And the second is the horizon itself, right?
No. The second is the light ring.
No.
Is a what?
It's the light ring.
It's a light ring. Okay.
Yeah.
That now I understand. All right.
That's right. So in these pictures, the horizon doesn't actually exist. So you replace everything inside this firewall with some sort of a quantum fuzz that either there's nothing inside or there is something very non-classical object.
No, but the light ring is not stable.
The light ring is, why do you say light ring is not stable?
Maybe I misunderstand, right?
I'm not putting anything here. This is just geometry, right? So okay. Yeah, so all it is that basically, if you have this black hole, you could think of it basically as stuff that are bouncing off the surface of the black hole, and they would bounce. So if there was just a standard horizon, they would just fall through the horizon. But if I put this firewall, they would just bounce around like a ball that bounces around on the surface of Earth. And the angular momentum barrier is really just the gravity of the black hole that bends back the gravitational waves so that it cannot escape. Right, so that's what this is. So you're not putting any physical object there. This is just the gravity of the black hole that's bending it back, right?
Okay. All right, thanks.
Okay, thank you. Any other questions? Okay.
If not, thank you again for showing up for the online talk. And like I said, we'd be happy to have you come physically whenever that is possible.
Thank you very much. It was a pleasure talking to you. Thanks a lot for the invitation. I was gonna stop the, did I stop sharing?